200. Here, we're going to look at the equilibrium aspects of acid-base chemistry, dealing with weak acids and weak base. Dealing with strong acids and strong base is stoichiometric, okay? And that's because when you have a strong acid and strong base, everything occurs at 100% of the time. So in this discussion here, we'll look at some of the fundamentals that you guys should have learned in Chemistry 200 and 152. If it's a little bit rusty, that's fine. We will be discussing this in today's discussion. Okay, so let me go ahead and let's see. Move that out of the way. So the first thing that you guys should realize is that acids are going to be those chemicals that tend to be reacts with bases, and here are some of the properties. Acid, they taste sour, they dehydrate substance. What does dehydrate means? It means that it removes the water, okay? It neutralizes bases, it dissolves metal, and then some examples are tomato juice, orange juice, apple juice. The main acid in orange juice, of course, is citric acid. You also have tartaric acid. So these are examples of chemicals that deliver hydrogen. Other items out there that are acidic are like wine, banana. Banana is actually slightly acidic. Coffee, vitamin C is nothing more than ascorbic acid. Sodas have a lot of phosphoric acid and citric acid, as well as carbonic acid. In fact, the carbonic acid breaks down to water and carbon dioxide. That's why you have a lot of carbon dioxide in your beverage. So these are examples of, these are the properties of acids. Bases, they tend to taste bitter, okay? They denature proteins. That means that the proteins, tertiary and quaternary structure starts breaking down. And then if the structure breaks down in proteins, then they're rendered worthless. That's why you should never handle liquid plumber or Drano, because those are actually just base, or sodium hydroxide with your hands, because it'll eat the proteins in your fingers and then it'll be a bad base burn. They certainly neutralize acids, and then they turn metals to hydroxides. So what is metals to hydroxide? If you take a metal and you put it in a base, they tend to like form like sodium hydroxide, lithium hydroxide, aluminum hydroxide. They react with metals in that fashion. Examples are milk of magnesia. If you ever have acid reflux, then you take a acid neutralizer like Tums or milk of magnesia. So they tend to neutralize acid. Lime water, it's actually basic. Like I said, Drano, liquid plumber, lye is nothing more than a base. Ammonia, your blood's slightly basic, and soap is also basic. Okay, so those are just examples and properties of base. This particular video shows what happens when you put carbon dioxide in water. The reaction is actually this right here, CO2 plus H2O. You guys can watch it if you look at the PowerPoint, but it's CO2 plus H2O forms carbonic acid. Carbonic acid breaks down, and if you have too much carbonic acid, like in your blood, that we will talk about later, it breaks down to water and carbon dioxide. So this is an equilibrium. But carbon dioxide in the air actually makes rainwater slightly acidic because it forms carbonic acid. This breaks down to hydrogen ions and the bicarbonate polyatomic ion. So you guys will learn all that in this particular chapter. First thing that you guys need to remember, however, is how to name these acids. So it's very important that you go back and review maybe your general chemistry or your Chem 52, or just take a look at these slides right here. Okay. Remember that oxy ions, well, there's a lot of acids out there, but the common ones are the halogenated acid. That is, if you have a halogen, fluorine, chlorine, fluorine, chlorine, bromine, iodide. Then you get HF, HBr, HI, etc. And there's the oxy acids, and oxy acids are formed by oxy ions. You guys know some of these oxy ions: SO4 minus 2, NO3, PO4 minus 3. These are oxy ions because they have oxygen in them. And then a second element, non-metal generally. So these are oxy ions. You should remember your oxy ions because then you will be able to remember your acids when hydrogens are attached to these things, like that. Okay, of course the charge is removed when you add a hydrogen. So just make sure that you review your oxy ions, or at least get yourself a good set of a list of oxy ions. So let's take a look at naming these acids. Remember that I'll give you an example of these oxy ions. ClO3 is chlorate. If you add an extra oxygen on that, it's perchlorate. If you remove an oxygen from that, it's chlorite. And if you remove another oxygen from that, it's hypochlorite. Anyway, if you know the oxy ions, then you can easily name the acid, because then the perchlorate ion, I mean the the perchlorate ion becomes perchloric acid. So HClO4 is perchloric acid. HClO3 is chloric acid. HClO2 is chlorous acid, and ClO is hypochlorous acid. So again, if you know the pattern, you know the trend, then it's easy to remember these family of acids. But let me go ahead and give you some of these examples. So you should recognize that. That's a very common acid. You guys have seen this acid in the lab. That's nitric acid. One less oxygen, NO3 becomes nitrite, but it's now called nitrous acid. H3PO4, you guys should recognize that. That's phosphoric acid. But H3PO3 is phosphorus acid. Notice that one is IC, the other one's OUS. That right there is perchloric acid. I already talked to you guys about these family of acid. This is chloric acid. Recognize that trend. We're going from here to here to here to here in naming these series of acids. That right there is chlorous acid. That right there is hypochlorous acid. Other acids out there is hydroiodic acid. Know the difference between hydro and hypo. Okay, hypo means lacking. So when you go from ClO2 to ClO, you have one less oxygen. That's why it's called hypo. Hydro means hydrogen. So know that difference, because that's a common mistake that I see a lot. That's hydrofluoric acid. That's carbonic acid. That is hydrocyanic acid. That is acetic acid. And these are dichromic acid. Okay, so make sure that you guys know how to name these things, or at least know the formula from the name, because sometimes you get an example a problem in which all we do is tell you what chemical you have, and it's up to you to use your chemical knowledge to write down the formula. Okay, so go ahead and continue here. There are really three definitions of an acid, and you guys have probably seen two of these or three, depending on the extent of your general chemistry first semester. First of all, the simplest definition is the servant Arrhenius. Yes, that's the same guy that gave us the Arrhenius equation in kinetics. He said that acid increased the hydrogen ion concentration. So anything that increases hydronium is acidic. Base increase hydroxide ion concentration. Anything that increases hydroxide are base. So these chemicals actually need to have H in their formula or OH in their formula. A more broad definition is acids are proton donors. Remember that hydrogen, the element, has one proton and one electron in its atomic configuration. When that electron is removed, what you have left is a proton. So a lot of times we say that hydrogen ions are nothing more than protons. In the context of chemistry, however, hydrogen ions or protons are not very stable. They're very reactive. So they need to bind to another chemical to stabilize it. And that's what you'll see in the next slide is that H plus doesn't exist by itself. It actually latches on to generally the solvent, water. And instead of just having H plus, you have H3O plus, hydronium. So whenever we say H plus, we actually are referring to hydronium in an aqueous medium. So I'll show you that in the next slide after this. The third definition is the Lewis, and we just define it in terms of the opposite of Bronsted-Lowry. We don't define the acid as a proton donor or proton acceptor. We define it as an electron acceptor or an electron donor. So it's just the opposite. You see how acids are donor here? In electrons, in terms of electrons, they're acceptor. Okay, base are a proton acceptor, but in the Lewis definition, they are electron donors. That's why ammonia, in which you guys know the Lewis structure, it's considered a base because it's got a pair of electrons to donate, but also it can attach a hydrogen. Okay, there's a side there for the hydrogen, and that side is the lone pair. So in general, base will need lone pairs so that the proton can latch on and be stabilized that way. So that's a little bit of insight on acid-base chemistry. So let's take a look at the Arrhenius definition real quick. In this particular case, acids increase hydrogen ion concentration, base increase hydroxide. What you have, an example of that is sulfuric acid. Sulfuric acid, and you guys should know that sulfuric acid is H2SO4. When you put it in water, it readily dissociates 100% of the time. This reaction in which it releases its hydrogen is practically stoichiometric. When I give you the term stoichiometric, I mean that it does it 100% of the time. Okay, that's what we mean by stoichiometric. When it's not stoichiometric, it's generally an equilibrium. So base, however, are going to be chemicals that accept hydrogen and, in the Arrhenius definition, they increase hydroxide ion concentration. So an example of a base would be like sodium hydroxide. Sodium hydroxide, when you put in water, will release hydroxide ions. So that's considered an Arrhenius base. So what are the factors that affect acid-base strength? Well, we need to go back to equilibrium, okay? Remember that when something does it 100% of the time, like a salt dissolves 100% of the time, like sodium chloride, if you don't get to the solubility limit, then that particular salt, that ionic substance, for every 1 molar of it that you have will give you 1 molar ions, excluding the Van Hoff factor. You guys need to go back to chapter 13 and remember what the Van Hoff factor is. But in an ideal situation, you get sodium chloride, you put it in water, you get um, equal amounts of sodium and chloride. We consider these strong electrolytes because they break up 100% of the time. They dissociate 100% of the time. So weak electrolytes, however, you put it in water and they do not do that 100% of the time. You take a chemical that's hardly insoluble, for example, maybe only 1% or 0.05% breaks up into its ions, the others stay intact. That's what we consider a weak electrolyte. It's still considered an electrolyte because you still generate ions in solution, but it's weak because it doesn't do it stoichiometrically, okay? On the other hand, something that doesn't dissolve is going to be, or doesn't break up, is going to be considered a non-electrolyte. Zinc oxide is a great example. Why do you think you wear it? To block out the sun rays, because then when you go to the ocean, it doesn't wash away. Okay, but anything that doesn't generate either ions or doesn't break apart are considered weak non-electrolytes. So let's take a look at a little bit of the chemistry. Perchloric acid, HClO4. You put that in water, it dissociates 100% of the time. It's considered a strong acid. Strong electrolyte acids are considered strong acid. Weak electrolyte acids are considered weak acids, however, because they don't do it stoichiometrically. They don't do it 100% of the time. So perchloric acid, chloric acid, nitric acid, those are all strong acids. An example of a weak acid is H2S or even HF. HF is a weak acid, and you'll see why later on in our discussion. Okay, so base are going to be chemical that generates hydroxide. They dissociate 100% of the time. On the other hand, weak base are chemicals that don't give up hydroxide or generate hydroxide 100% of the time. Sodium hydroxide and calcium hydroxide are considered strong base. On the other hand, ammonia, and if you notice, ammonia itself doesn't have hydroxide in its formula. The key there is that it reacts with water, the solvent, and then it generates hydroxide. But this is not 100% stoichiometric, and so it's considered a weak base. So when we say strong and weak, we're not talking about concentration. What we're talking about is the chemistry. Okay, so please remember that. Strong and weak acids, strong and weak base, it's not about the concentration. It's not how much you have. It's about the chemistry and their dissociation or their ability to break up or take in certain species, functions at 100% capacity. If it's very efficient, stoichiometric, it's strong. If it's not very efficient, less than 100%, even if it's 90, it's considered weak. Okay. So strong acids, 100% dissociation. Remember this right here, because these are the 7 strong acids that you guys need to commit to memory. If you remember these 7, then you would consider practically everything else as weak. So it's better to remember the few strong ones, rather than all the acids and bases. So if you remember these 7 strong acids, then you could treat other acids as weak. Okay? So sulfuric acid is a very strong acid. The first hydrogen that comes off does so 100% of the time. Remember that sulfuric acid has 2 hydrogens to donate. The second hydrogen doesn't come off 100% of the time, however. Okay? Perchloric acid is a strong acid. Chloric acid is a strong acid. Nitric acid is a strong acid. And then the halogenated acid, with the exception of HF. HF is not a strong acid, but HCl, HBr, HI are all strong acids. In lecture 3, we will see the reason why these are strong acids. Remember that strong acids are acids that give up their hydrogen 100% of the time. That means weak acid holds on to their hydrogen much more strongly. That means their bonds are strong. The bonds between the hydrogen and the ions here are weak. That's why the hydrogens can come off. And remember, that's what we define as an acid, the ability to give up that hydrogen. The more willing it can give up that hydrogen, the stronger that acid happens to be. Okay. Let me also mention that even though there are the chemicals not listed here are considered weak, there are different degrees of weak acids. You can have a strong weak acid, or you can have a very weak acid. They're considered weak because they don't give up their hydrogen 100% of the time, but a strong weak acid will give up their hydrogen, say 90% of the time, versus a very weak acid that only does it like 0.5% of the time. Okay, so there's different degrees of weak. There's only one degree of strong. These are all considered strong. They all do it 100% of the time, and you can consider them all at equal strength. So only strong acids will dissociate 100% of the time. The Ka is much bigger than 1, in other words. Strong bases, likewise, the reaction will be 100% dissociation. Again, H2S is a weak acid. They dissociate. They give up their hydrogens less than 100% of the time. So remember, I just mentioned that there's different degrees of weak. Some will do it 90% of the time. Some will do it 70% of the time. A lot will do it less than 1% of the time. Well, how do you determine which weak acid are stronger or weaker than say one versus the other? It's an equilibrium problem. The ability for this thing to give up its hydrogen is an equilibrium. So that equilibrium constant is huge. That means that it's a strong, say, weak acid. It's going to be less than 1, but if it's a number, say when you're comparing two chemicals and that particular K equilibrium, we call it Ka, by the way, A for acid. If that number is bigger versus what you're comparing it to, then it's a stronger weak acid. Okay, I know that's an oxymoron, but remember that weak is defined by its ability to give up its hydrogen 100% of the time. It doesn't do it 100% of the time, but it does it more efficiently than another chemical. So we need to look at the equilibrium constant, and that's exactly what this is. Look at the Ka's in this table. It's in your book as well. But here you can see the equilibrium constant for these chemicals right here to give up the hydrogen. In this particular chemical, this is iodic acid. This hydrogen is the acidic. That's the one that's released. In fact, in all of these, it's the hydrogen in red that is the acidic hydrogen, because some chemicals will have more than one hydrogen and you might get confused as to which hydrogen is donated. Like, for example, that it's generally the one attached to the oxygen. Okay, it's generally the one that's attached to the oxygen. That's the acidic acid. That's the one that comes off. So look at these Ka values. This is 1.6 times 10 to the minus 1. This is 1.0 times 10 to the minus 10. So based on these Ka values, this is a bigger number. They're still less than 1, okay? Like this is 0.16. So that's why these are weak acids. But 1.6 times 10 to the minus 1 is a bigger number than 1 times 10 to the minus 10. So therefore, iodic acid is a stronger weak acid than phenol. Okay, it's a stronger weak acid than phenol. Phenol, you guys have this, by the way, in your activity that you guys are scheduled to do this later tonight. For those of you in my lab, phenol is an acid. This hydrogen comes off, but it doesn't come off very efficiently. Look at the Ka, the equilibrium constant for that hydrogen coming off. It's only 1 times 10 minus 10. Look at hypoiodus. It's 2.3 times 10 to the minus 11. It's even less efficient than phenol, and it's definitely less efficient than iodic acid. Okay, so again, we're using numbers here to quantify the strength of these acids. So in terms of increasing strength, it goes up because the Ka for the ones on top are larger than the Kas than the ones in the bottom. That's what makes it a strong weak acid or a weak acid. Okay. So bases, remember I said that in the Arrhenius definition, those are the ones that give up hydroxide. And go back to the solubility rules. And hopefully you guys remember that, especially for this weekend, because one of the statement in the solubility rules is all alkali. Alkali are group 1 um, ionic substance are going to be soluble in water. That means like lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are all group 1. That means they're soluble in water. That means that they break up into their ions 100% of the time. That's why these guys are strong bases, okay? Because they're stoichiometric in the amount of hydroxide that they generate. Then heavy group 2. Heavy simply means that their atomic weight is heavier than magnesium, like calcium, strontium, rubidium, any element that is lower than calcium in terms of the periodic table, so more massive, equal the atomic weight of calcium or higher, okay, are considered heavy group 2. Well, heavy group 2 are considered very soluble. And if you guys want to know about the chemistry, it's because it's a bigger atom, the electrons are further out, and so the hydroxide that is binding to the metal are further out, so there's less pull, and so that interaction, that electrostatic interaction is weaker, and so that's why those hydroxide can break off more efficiently. Well, anyway, for heavy group 2, these are all strong bases, but be careful because if you've got 1 molar calcium hydroxide, you do not generate 1 molar hydroxide. And the reason why is because of the formula. Calcium hydroxide is Ca parentheses OH2. So for every 1 molar calcium hydroxide, theoretically, you get 2 molar hydroxide, just based on the stoichiometry. Don't ever forget about the chemistry because that's where you're going to get some mistakes in terms of doing some calculations, okay? Ionic metal hydroxides or metal oxides are also basic. And the reason why that's the case is because, again, anything that's alkali is 100% soluble in water. So if you take a look at this chemical right here, or you can substitute sodium hydroxide in water, what will happen is that the hydrogen will attack that oxygen. And what you get is OH, and here's another OH, and you get 2 lithium left behind. Okay, so that's how hydroxides are formed from these alkali metal oxides. And that's why they are strong base. And again, look at the chemistry. For every 1 mole of lithium, 1 molar lithium oxide, you get 2 molar hydroxide because when water reacts with it, water itself gives you a hydroxide, and then the hydrogen from the water reacts with the oxygen on that oxide and generates a second hydroxide. So please remember the chemistry because for every 1 molar lithium alkali oxide, you get 2 molar hydroxide from that reaction. So let me clear this up real quick. And these are bases which dissociates 100% of the time. And so if it's not in this category, then you can consider it a weak base. Okay. And the most common weak base that you will see are when you have a weak acid in which the hydrogen has been removed. What do I mean by that? Let's say I have HF. When that gives up its hydrogen, it becomes F and H plus. Remember, this is an equilibrium. Bases are chemical that wants to absorb or attract hydrogen ions. So in the reverse reaction here, it's going to be a proton acceptor. And so this chemical is considered a base because in the reverse reaction, remember what you have in a beaker of water, when you add HF, is not only HF exclusively, you also have F minus and H plus and H2O. Well, this chemical right here is going to be a base in that solution. Yeah, you have some HF, but you also form F minus. And if you could isolate that F minus, you find out that that particular F minus is a weak base. Okay. In fact, that's what you will see in next week when we talk about conjugate acids and base. The conjugates of acids are generally base. Conjugate just means adjoining to. Okay. So F minus in this particular example is going to be the base in the reverse direction. Remember that when we have weak acid, weak base, we're talking about equilibrium. Whenever we have strong acid, strong base, we're talking about stoichiometry. It only goes in the one direction, reactant to product. So here are examples of strong base, strong. Here, strong base is produced. Calcium oxide reacts very readily with water. You get a strong base, and then this will break down to calcium and hydroxide in aqueous medium. So these are some of the chemistry that hopefully you guys covered back in general chemistry, chemistry 1. This is an example of a weak base, ammonia. Why? Because it doesn't generate. If you have 1 molar ammonia, you do not get, okay, 1 molar hydroxide. That's why it's considered a weak base. Okay. So let's take a look at this right here. This is hydrochloric acid. And in this example right here, let me show you this in my PowerPoint slide so that it's much easier to see the video on this, because I really want to demonstrate what's going on here. So let me pull that to my computer and then share that slide with you. Here it is. Let's see. So in this particular example, here it is. Let me change view. We're here. Let's take a look at this real quick. I'm just going to blow this up so it's easier to see.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte or weak acid.
So notice the difference. When a strong acid dissociates or breaks apart, they stay apart. When a weak acid dissociate, they can reform. Okay, the reverse reaction can occur. That's why it's an equilibrium. All weak acids, weak base involves equilibrium. You need an equilibrium constant. Don't look for an equilibrium constant for strong acids. Why? Because it's stoichiometric, and you guys that's why you guys were able to cover acid-base chemistry in general chemistry 1, because you didn't have to worry about equilibrium concept. Here you do. Let's take a look at the second movie here. Okay, and then this will hopefully give you more clarity in terms of bases. Let's take a look at that.
Bases are substances that increase the concentration of hydroxide ion in water. Water soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
Again, ionized just means that it's charged. Okay, so let me go ahead and go back to my iPad and continue our discussion from there. Okay, so hopefully that visual kind of help you understand what we're talking about in terms of the chemistry. You really got to understand the chemistry in order to do a lot of the problems, because right now we're just looking at the chemistry, and then later on we're going to quantify it and calculate how much hydronium ions do you get. If you know the hydronium ions, then you can calculate the pH of the solution. Okay, you can tell me whether the solution is very acidic or slightly acidic just from the pH. So these are the things that are important in acid-base chemistry, but you need to understand the chemistry, the fundamentals, in order to be able to understand how the math tells you the story. So hydrochloric acid, remember, is a strong acid, but you can't just take pure hydrochloric acid. You can't make it. You can make pure hydrochloric acid uh, via the gas state, but in reality, you make hydrochloric acid in the aqueous state. And so when it dissociates, it produces hydrogen ion and chloride ions. And I remind you again the atomic structure, or the atomic structure of a hydrogen atom. A hydrogen atom has one proton, that's what you see here, and one electron. When that electron is removed, and why is that electron removed? Because the electron stays behind to the chloride. Okay, remember that hydrogen has one electron to donate. Chlorine has 7 electrons. When they form this covalent bond, that one electron from the hydrogen and the unpaired electron from the chlorine are shared. But now when that hydrogen is removed, it leaves that electron behind. And so what you have is not a hydrogen atom anymore. You have a hydrogen ion, which is really a proton, But I told you that that proton's not very stable. It needs to stabilize itself. So it attacks water. It attacks water because water has lone pairs like that. You guys remember the Lewis structure. So when you have a hydrogen ion, it's going to stabilize itself with a pair of electrons. It doesn't want to stabilize itself and go back to chloride. In fact, chloride, because it's so much more electronegative, wants to hold on to that electron. Hydrogen, on the other hand, remember that oxygen is electronegative, but it's already distributing its electronegative negativity to the other hydrogens. So those electrons right here are available for that proton to stabilize itself on. And so that's essentially what we have. In reality, when we say about hydrogen ions or protons in aqueous medium, we're not really talking about protons or hydrogen ions. We're talking about this guy right here. And that guy's called hydronium. But in chemistry, we use the term interchangeably, protons and hydronium. For the most part, we say, when we say a proton in aqueous medium, we're really referring to hydronium, but that's just the vernacular of the field. Okay, you guys already know at this from this point on that it's not really a proton that's swimming in water. It's actually a hydronium because that proton is unstable. It needs to stabilize itself with the most abundant chemical in that medium, and the most abundant chemical in that medium happens to be water. Remember that in general chemistry 201, most of the solvent, almost all the solvents we are dealing with is aqueous medium, water. So that's what I want to illustrate here. Hydronium ion can actually become more complex. This is hydronium ion, and what it'll do is it'll hydrate with other water molecules through this idea of hydrogen bonding. Okay, you guys hopefully remember hydrogen bonding. We talked about that in chapter 11. But in a situation like this, hydronium hydronium can also be um, written out this way. It's not common because you guys don't have to worry about it, but know that this chemical right here has 3 oxygens, and it's got 7 hydrogens, and it's a cation. Okay, it's just hydronium with 2 other waters attached via the hydrogen bonding through hydration. Anyway, that's what we see a lot when we do more investigation. For the most part, you guys just need to remember protons, hydrogen ions are really hydronium. So let's take a look at the chemistry of water. And this is really important. And it answers the question, why does water have a pH of 7? And not just water that you get from tap, because that doesn't have a pH of 7, or water that comes from the sky, because that doesn't have a pH of 7, but water at 20 degrees, pure water with no contaminant. It has a pH of 7. Why 7? Why not 5 or 50 or 100? Where did that 7 number come from? Okay, where did that 7 number come from? And you guys will be happy to know it comes from what you guys already learned from chapter 15. It comes from the equilibrium constant of water chemistry. So let's take a look at water. Water, and what we have right here is 2 molecules of water, but water actually reacts with itself, plays with itself. And what water will do is that water, and only 2 in 1 billion will do this type of chemistry, by the way. Only 2 in 1 billion. And so we say that because water can either give up a hydrogen or accept a hydrogen, we say it's amphoteric. Amphoteric means that it acts as an acid or a base. The same chemical can act as an acid or a base. Water can donate a hydrogen or accept a hydrogen. And how does it do that? Well, let me just show you that. This is the Lewis structure of water. And this is the Lewis structure of a second water. What will happen is this hydrogen will come off and attach to that second water, the lone pairs. Remember, this is not very, this does not readily occur. Only 2 in 1 billion. If only 2 in 1 billion does this reaction, you know that the equilibrium constant for this reaction is very, very small. Okay? It's because it doesn't happen readily. But if you're talking about moles and moles of water, remember 18 milliliters is 1 mole. And if you have a gallon, you definitely have moles and moles of water. Then there's a lot of chemicals in that batch that does this reaction. What you get here is this guy. Let me change my color here. This guy right here becomes this right here. And isn't that H3O plus? And this guy right here becomes, and isn't that OH minus? So that's the chemistry of water. And it does, when you form hydronium, you form an equal amount of hydroxide. You can't have 2-to-1 ratio, because by giving up a hydrogen, that chemical that gave up the hydrogen is going to be a hydroxide. And by giving up the hydronium, you form one hydronium. So they form in equal amounts. So let me clear this for you. You form hydronium and hydroxide. This reaction, by the way, is endothermic. You increase the temperature, that reaction occurs more readily. And this is the thermicity of the reaction. It's 55.9 kilojoules per mole. And the equilibrium constant, which we call Kw, is the equilibrium constant for this occurring. And this is the values at different temperature. 25 degrees, it's 1.01 times 10 to the 14th. Okay, so the reason why this is important is because we generally quote our system, our aqueous medium, at 25 degrees. If we were to quote it at different temperature, then we would use a different equilibrium constant. Notice how the equilibrium constant becomes bigger at higher temperature. That's how we know it's an endothermic reaction. Okay. Remember this list, because whenever I tell you, say you have an acid-base chemistry problem and it's not at 25 degrees, then you got to use a different equilibrium constant. But let me explain how this number 7 came about. Okay, let me explain how that number 7 comes about. So the consequence of autoionization, and that's what this is, by the way. This right here is what we call an autoionization reaction, because it automatically does it in the tune of 2 in 1 billion, in the tune of 1 times 10 to the minus 14 at 25 degrees. It's actually 1.01 times 10 to the minus 14 at 25 degrees. So it's called an autoionization because you don't really need to initiate it to get it going. It just occurs. So the consequence is that when you have more hydronium in your medium, then it's considered a acidic solution. When you have more hydroxide, it's considered a basic medium. So, and these two are going to vary depending on whether your solution is acidic or basic in a proportion, because your medium is water. If you just have plain water, they're equal, okay? But if you put in another chemical and make the solution more acidic, then the hydronium ions will increase, the hydroxide ions goes down. There's always going to be, when one goes up, the other one goes down. So acidic solutions are generally solutions in which hydronium is greater than hydroxide. Neutral solutions are when hydronium and hydroxide are equal, not when its pH is 7, by the way. Okay? Need you to understand that. Neutrality does not necessarily mean pH 7, because you don't get pH 7 at higher temperatures. Okay? If the Kw was 1 times 10 to the minus 16, then neutrality would be pH 8. Well, Neutral, by definition, is when you have equal amount of hydroxide and hydronium. That's the clear definition of neutrality under acid-base chemistry. Basics when hydroxide is greater than hydronium. And we have this relationship, okay? This particular diagram sort of helps you make that understanding. But let's take a look at the chemistry of water, okay? Uh, Let me
Can you
do
go back to
this,
that last slide?
this slide right here. Yeah. Whenever you have hydronium or hydroxide, when they're equal, it's neutral. When hydronium is bigger, it's acidic. When hydroxide is bigger, it's basic. And this slide will become more obvious after I do the next discussion, okay? I've got a better slide than this in the next few slides. So, but this is an important slide. So I'm gonna do this by hand because I really wanna watch. Really want you guys to see how this works. You have water, and you've got two waters forming, and these are liquid. You know it's an endothermic reaction, and you know it's an equilibrium, and that equilibrium, say at 25 degrees, we got to define the temperature, is going to give us hydroxide, and that's aqueous. Why? Because the hydroxide are going to be stabilized by the water molecules because this is charged, and we get hydronium, and that too is aqueous. Well, isn't this really nothing more than an equilibrium as defined by that double arrow? So we can write K equilibrium, which is really Kw, which is really 1.01 times 10 to the minus 14, okay, is equal to the products, hydroxide times hydronium. And then we don't leave out, we don't put in our mass action expression. We don't put in our mass action expression water because it's a liquid. Concentration of water is constant. So this problem right here we can solve because hydroxide and hydronium are equal. You form equal amount. Again, this is pure water at 25 degrees. So we can make this x squared. This is nothing more than x. And that's 1.01 times 10 to the minus 14. And if we solve for x equals 1.0 times 10 to the minus 7. So the amount of hydroxide and hydronium in pure water at 25 degrees comes to the tune of 1.0 times 10 to the minus 7 molar. It's a very small amount, but it's still there, okay? The concentration are equal because it's neutral, but the concentration, if we have an equilibrium constant of 1 times 10 to the minus 14, comes out to 1 times 10 to the minus 7. If it wasn't 1 times 10 to the minus 14, let's say that this is 1 times 10 to the minus 16, then guess what? The x value here would be 1 times 10 to the minus 8, okay? So that amount of hydronium and hydroxide depends on the equilibrium constant. Now, it just so happens, I gotta erase this page, okay? It just so happens that 1.0 times 10 to the minus 7 molar, either in hydroxide or hydronium, is too difficult for the general public to understand. You gotta remember that most of America out there do not like science, and therefore they do not like math. And so a number like this is very intimidating. So what do scientists do? They try to dumb it down. And one of the ways we cannot dumb this down is introduce a function. Yeah, the function's complicated, but the result is simple. And what we can do is we can take the negative log of this number, this very complicated number, 1 times 10 to the minus 7. We take the negative log base 10. And if you do that in your calculator, guess what it spits out? It spits out the number 7. So pure water has a pH, and that's what we call the pH. It's called the power of hydrogen when you do the power function. remember that the inverse of log is 10 to the x. Okay, so if we take 10 to the minus 7, that'll give us 1.0 times 10 to the minus 7. That's the inverse of the log base 10 function. But the whole idea here is that what we have is we take a number like 1 times 10 minus 7. It has a lot of zeros. 1 times 10 to the minus 8. 3.46 times 10 to the minus 4. Something that's exponent. And we convert it to something that's easily digestible, like 7. That's why neutral water has a pH of 7. But only neutral water that is pure, and that is at 25 degrees. That's where 7 comes from. Okay. So let me clear this. And this is the derivation for that. Okay. And we can solve for that. And certainly we can do that. Make sure you know how to do these types of function in your calculator, because that's what your calculations will be for the most part. Okay. So I'm going to skip over this because you guys can read it and then practice it on your calculator. What I want to show you again is that this is the number that we have. This is at 25 degrees. The concentration of hydronium is 1 times 10 to the minus 7. When you take the negative log of that, it's 7. The important thing that you should know here is that the pH plus the pOH is equal to the pKw. So if you take the negative log of 1 times 10 to the minus 14, that equals 14. So that's why 7 and 7 equals 14. But look at what happens when you have an acidic solution. Your pH becomes small when you have an acidic solution because your hydronium ions are high. When you have a 1 molar hydronium ion, then the exponent is 1 times 10 to the 0. When you take the negative log of 1 times 10 to the 0, that's 0. That means the hydroxide has got to be 1 times 10 to the minus 14. Okay? Because 1 times 10 to the minus 14 times 1 equals Kw, which is 1 times 10 to the minus 14. So if you take the negative log of 1 times 10 to the minus 14, that's 14. Anyway, you can see that relationship easily. The pH plus the pOH always equals 14. If you have a nice clean number like 1 times 10 to the minus 4, 1 times 10 to the minus 6, you can easily come up with the pH in your head. But if you have a number like 8.47 times 10 to the minus 3, you can't get the pH from that readily in your head. You actually need to go to your calculator. Just punch it in. You punch this number, 8.47 times 10 minus 3 in your calculator. You hit your log button, log base 10, and then you take the negative of that, and that's your pH. Okay? And here you can see that very basic solutions, your concentration of hydroxide is 1 molar. That means your hydronium is 1 times 10 to the minus 14 molar. If you have a 1 molar hydroxide solution, its pH is going to be 14, but its pOH is 0. It's pOH. Okay? If you know the pH of a solution, you easily can figure out what the pOH is, as long as you know also the Kw. Okay? Let me go through this because the P function is very important. The P function basically just takes a number and takes the negative log of that. You can do the P function for hydronium. You can do the P function for hydroxide, in which case you get pH or pOH. You can take the P function for any equilibrium constant. And then you get the pK equilibrium. For water, it's called the pKw. For acids, if you take the negative log of a Ka, it's called pKa. Make sure you know how to do this, because a lot of times in a problem, we don't quote you the Ka, we quote you the pKa. How do you get the Ka from the pKa? Well, you just take 10 to the minus pKa value and you punch that in your calculator. You take the negative of the pKa and you raise it to the 10th power. That's the inverse of the log. Okay? So again, P means the power function. And this is the slide that I was trying to get at. The relationship between hydronium and hydroxide is this equation. Hydronium times hydroxide equals Kw. So if you're given hydroxide and you want to calculate hydronium, then just take the Kw that you know and divide by hydroxide. If you're given the hydronium and you want to calculate the hydroxide, then just take the Kw and divide it by hydronium. It's a simple math operation. The relationship between pH and pOH is even easier. pH plus pOH equals pKw at 25 degrees equals 14. So just subtract 14 from the pOH, you get the pH. Take 14 and subtract pH, and you get the pOH. It's very easy. I like this route much more than I like this route. Okay. Um, that is your P function. You take the negative log, and that is your inverse function, 10 to the minus pH. You can do that for pOH as well. Okay, so given any one of these, if I'm given the hydroxide ion concentration, let's say that my hydroxide ion concentration is 1.0 times 10 to the minus 3, then I already know what my pH is. My pOH, it's 3. I already know what my pH is. It's 14 minus 3. That's going to be 11. And then I know what my hydronium is. That's just 1 times 10 to the minus 11. Okay. So given any one of these, you guys can calculate the other three. And since I started out with an easy number, I can do that off the top of my head. But if I give you a number like 3.7 times 10 to the minus 4, then you'll need your calculator. But this is a very handy chart to have because it shows you the relationship of all the variables in acid-base chemistry. Okay, so this is just an example of that. I won't go through that because it's nothing more than the math, but make sure you know how to do that in your calculator. What I found in the past is that you guys understand the concept, you're punching it wrong in your calculator. So please practice this. Okay, here are more practice problem. What I want to finish up with in this discussion is a little bit about the environment, and then I'll talk to you guys about that problem that I assigned. Rainwater. Like I said, when it's falling from the sky, water, initially it forms pure water, but as it falls through the sky, it actually is going to absorb carbon dioxide. And as it absorbs carbon dioxide, you form carbonic acid. So rainwater really is not neutral at 25 degrees. It's not a pH of 7. It's actually acidic. It's going to have a pH of somewhere around 5.8 to about 6.3 because you're forming carbonic acid from the carbon dioxide. What's more important to us is not so much rainwater, but pollutants. If back in the 80s, when you have a lot of coal burning power plants, you release a lot of sulfur trioxide because coal has a lot of sulfur in it because it comes from plants. And so plants have proteins in them, sulfurs are in proteins. And so when you burn coal, you form sulfur trioxide. Look what happens when rainwater mixes with sulfur trioxide. This is the chemistry that occurs. Sulfur trioxide plus water gives us sulfuric acid. So if you were in, say, Wheeling, West Virginia or Kentucky where they burned coal and it was polluting the air and it rained, guess what? Battery acid is hitting your head. So that's why we sort of minimize the burning of coal, or at least we scrubbed out the sulfur from coal because it was very dangerous to our environment. Of course, we don't live in the East Coast where they burn coal. They're actually tapering that down now, thank goodness, because it's harming our environment. But we do live in the West Coast where we love our cars. And when we burn gasoline, we form nitrogen dioxide. That's why we have smog checkup, because we need to minimize the form of nitrogen dioxide or oxides of nitrogen. But look at the chemistry of when nitrogen dioxide reacts with water in our atmosphere. It forms these two chemicals, nitric acid and nitrous acid. So when you see that brown haze above LA, like especially in the 90s, I remember driving through that, and it rains, guess what? Nitric acid is hitting your head. Again, that's why we have the smog controls because we don't want this in our atmosphere. Look what happened to poor old George. This was George Washington in 1944. But over the years, because of our environment, it looks like he has leprosy. Okay. Basically, marble is nothing more than calcium carbonate. It's like chalk. When you put chalk in vinegar, it basically dissociates it. That's what happens. These are other examples of whole forests dying off because of pollutants in the air. Anyway, that's all I wanted to talk to you guys about in this particular discussion.